Hey Bob, I've been going through a big stack of quantum computing papers from April 2026, and honestly, there's a lot to unpack. The breadth of topics is striking, from fault-tolerant architectures to quantum machine learning to post-quantum cryptography. Where would you even start making sense of it all?
It really is a rich month. I'd say the most exciting cluster of papers centers on fault-tolerant quantum computing, specifically how close we might actually be to building machines that can do something classically intractable. A few papers stand out immediately. The Walking Cat architecture paper from Tripier and colleagues at IonQ and Microsoft is a landmark blueprint. They propose a full fault-tolerant trapped ion computer built entirely on LDPC codes, and they estimate that a device with just 10,000 physical qubits could simulate a 100-site Heisenberg model within a month, including all the shots needed for chemical accuracy. That's a concrete near-term target.
That's remarkable. What makes the Walking Cat architecture different from other fault-tolerant proposals? Is it mainly the choice of LDPC codes, or is there something more architectural going on?
It's really the combination of several things working together. The backbone is what they call a cat factory, a mechanism that produces cat states distributed throughout the machine, which are then consumed to perform logical operations. They identify three promising instances: a simple single LDPC code architecture, a fast architecture using a 70,769 process code with Clifford frame tracking, and a dense architecture using a 102.22 code that encodes 22 logical qubits per memory block. That dense design gets you 110 logical qubits and about a million T-gates per day, using only 2,514 physical qubits. What's philosophically important is that they deliberately emphasize simplicity over hypothetical peak performance, and they only use hardware components that have already been experimentally demonstrated.
That simplicity-first philosophy seems important for actually building these things. Speaking of neutral atoms, there was also a paper from Khan, Sethi, and colleagues on architecting early fault-tolerant neutral atom systems. How does that compare?
Great connection. The neutral atom paper from Khan and colleagues at Duke tackles a different bottleneck: the fact that spatially efficient quantum error correction schemes tend to be very serial, leaving a lot of unused space on the chip. They introduce a teleportation-based scheme that exploits the reconfigurable connectivity of neutral atoms to parallelize logical operations. The result is up to a 3x speedup over extractor architectures at no extra space cost. They then actually simulate compilation all the way down to gate scheduling and atom shuttling patterns, and they find that quantum advantage is achievable with as few as 11,495 atoms and a runtime of about 15 hours. So both papers are converging on the idea that early fault-tolerant advantage is within reach, but through quite different hardware and architectural strategies.
There's also a paper specifically on magic state injection for extractor architectures, Inject from Sethi, Khan, and colleagues. That seems to address a very specific bottleneck within those neutral atom designs.
Yes, Inject is a nice example of drilling down into a critical bottleneck. In extractor architectures, over 90% of total program error comes from the scintillation process, preparing and injecting T-states to implement non-Clifford gates. Standard RZ scintillation requires multiple sequential T-state injections, each requiring expensive intermodule measurements. Inject proposes a two-factory design that synthesizes RZ states with lower error rates and injects them using only a constant number of intermodule measurements. Combined with a prefetching strategy that prepares correction states in parallel, they report up to 22x reduction in error rates, 13x improvement in wall clock time, and 7.2x reduction in space-time cost. It's a very targeted engineering contribution that could be critical for making extractor architectures practical.
On the surface code side, there were several papers too. The workload-aware surface code architecture paper from Ghosh Chatterjee and Ghosh caught my eye. The idea of designing the floor plan around the T-gate profile of a specific application seems quite pragmatic.
That paper is a good example of moving from generic fault-tolerant designs toward workload-specific optimization. The key insight is that prior FTQC designs either optimize for fast logical qubit access at high qubit cost or high density at high latency. Their approach places surface code patches around an ancilla-centric region to give nearly uniform ancilla access for all data qubits, and then uses the T-gate profile of a specific application to determine the floor plan. They also introduce a reconfigurable optimization for Y-gate measurements on a per-workload basis. The results are impressive. Cycles per instruction near optimal while reducing required data tiles by up to 21% and up to 90% efficiency when running 10 programs concurrently. The multi-programming angle connects nicely to another paper in this batch.
You mean the no tile left behind multi-programming paper from Ghosh Chatterjee and Ghosh again? It seems like the same group is building a comprehensive framework for FTQC architecture.
Exactly. The multi-programming paper is a natural companion. They develop a formal framework for FTQC multi-programming that accounts for the structured floor plan of data tiles, ancilla tiles, and magic state service resources. The challenge is that concurrent execution in FTQC is fundamentally harder than in NISQ. Admission decisions can fragment the remaining floor plan, conservative reservations waste ancilla, and dynamic contention across resources degrades throughput. Their hierarchy-aware scheduling achieves a normalized system speedup of 3.1x and improves over prior FTQC multi-programming baselines by about 29%. Together with the workload-aware architecture paper, they're building a coherent vision of how to actually run multiple programs efficiently on a fault-tolerant machine.
There's also the Coval-Q paper from Liao, Takami, and Suzuki on SAT-based design automation for surface code logical operations. That feels like it's addressing the verification and optimization side of the same problem.
Right. Coval-Q is essentially proposing an EDA, electronic design automation, equivalent for fault-tolerant quantum computing. Just as chip designers use EDA tools to verify and optimize classical circuits, Coval-Q formulates surface code logical operations as a satisfiability problem. What's new compared to prior SAT-based frameworks is that it handles logical qubits with more flexible surface code encodings, including advanced layouts like fast blocks. They demonstrate that Coval-Q can determine the minimum execution time of fundamental logical operations, and applying these results reduces execution time of widely studied FTQC applications by about 10% under a simplified scheduling model. It's a foundational tooling contribution, the kind of thing that becomes essential as the field matures.
Shifting to the decoding side, there were several notable papers. The Scalable Neural Decoder paper from Gu, Bonilla-Ataides, Lukin, and Yelin seems particularly impactful. They're claiming logical error rates 17x below existing decoders for the gross code.
That paper is genuinely exciting. They introduce a convolutional neural network decoder that exploits the geometric structure of QC codes, and they probe what they call a waterfall regime of error suppression. For the 144 to 12 of 12, gross code at a physical error rate of 0.1%, they achieve logical error rates around 10 to the minus 10, which is 17x below existing decoders with 3 to 5 orders of magnitude higher throughput. The decoder also produces well-calibrated confidence estimates that can reduce the time overhead of repeat until success protocols. The broader implication is that the space-time costs of fault-tolerant quantum computation may be significantly lower than previously thought, which is a big deal for resource estimation.
The AI-based predecoder paper from Chamberlain and colleagues at AWS also addresses decoding speed and accuracy, but with a modular approach that pairs a local AI predecoder with any global decoder. How does that compare philosophically?
The two papers are complementary. Chamberlain's predecoder is designed for practical deployment, so it's back-end agnostic, completely open source, and achieves end-to-end decoding runtimes of order 1 microsecond per round at large code distances on NVIDIA GB300 GPUs. The key innovation is the modular architecture. The AI predecoder handles the majority of physical errors locally and in parallel, passing residual syndromes to a downstream global decoder. They also introduce a noise learning architecture that infers decoding weights directly from experimentally accessible syndrome statistics without needing an explicit noise model, which is critical for real hardware where noise is unknown or time varying. So Gu et al. Push the accuracy frontier, while Chamberlain et al. Focus on making AI decoding practical and deployable at scale.
There was also a cellular automaton decoder paper, Scala, from Winter, Guades, and Muller. Local decoders seem to be getting renewed attention. What's the appeal there?
Local decoders are attractive because they avoid the communication and data processing bottlenecks of global decoding strategies, which become severe at scale. Scala, which stands for Signaling CA with Local Attraction, is a non-hierarchical cellular automaton decoder for quantum repetition and toric codes. It achieves a code capacity threshold of about 7.5% on the toric code with strong subthreshold scaling, and crucially, the local computational resources remain independent of system size. That modularity makes it suitable for hardware implementation. They also show strong robustness to qubit measurement errors and noise within the decoder itself. The comparison with Harrington's hierarchical CA decoder is useful. It shows that non-hierarchical designs can be competitive while being simpler to implement.
The AI-enabled decoder for qubit loss from Wang, Nie, Dai, and colleagues at Tsinghua addresses a very different kind of error. Not poly errors, but actual qubit loss. That seems like an underappreciated problem.
It is underappreciated, and this paper handles it elegantly. Qubit loss is particularly nasty because it invalidates the algebraic structure of the stabilizer formalism. You can't just apply standard decoding. Their spatiotemporal graph neural network decoder performs a dual-head task, simultaneously correcting standard poly errors and identifying the locations of qubit loss from the flicker patterns in stabilizer measurements that loss induces. It outperforms both standard MWPM and even delayed erasure MWPM decoders that already have loss location information. It can identify over 90% of loss locations after accumulating measurements over 10 rounds, enabling qubit reinitialization. The parallel input structure also gives it an inference time advantage over modified alpha qubit. It's a robust framework for a problem that will matter a lot on neutral atom platforms where atom loss is a real concern.
Speaking of neutral atoms and LDPC codes, the ultra-high-rate quantum codes paper from Zhao, Duckering, Gu, Mascara, and Zhou seems like it could be transformative for qubit overhead. Encoding rates exceeding 1 Hz are dramatically better than the roughly 110 we typically see.
This paper is one of the most striking of the month. Building on a construction by Kasai, they identify new structural conditions on affine permutation matrices that make encoding rates above 1/2 compatible with efficient implementation on reconfigurable neutral atom arrays. The co-designed code family supports efficient syndrome extraction and atom rearrangement under realistic parallel control constraints. Using a hierarchical decoder, they achieve per logical per round error rates of about 10 to the minus 13 with a 2304,156 code, approaching what they call the teraquap regime. To put that in perspective, with over 1,000 logical qubits encoded in 2,204 physical qubits and error rates that low, you're looking at a fundamentally different resource landscape for fault-tolerant computing.
The networked QLDPC paper from Shaw and Rangaswamy also tackles the practical implementation of LDPC codes, but from a distributed networking perspective. How does that fit into the picture?
Shaw and Rangaswamy are addressing the non-local stabilizer problem from a different angle. Instead of trying to build monolithic hardware with long-range connectivity, they propose distributing the code across a network of nodes, with each node holding a subset of qubits. They focus on bivariate bicycle codes because of their similarity to surface codes and their controlled amount of long-range connections. They use balanced min-cut partitioning on the combined XZ-Tanner graph to find optimal qubit splits and implement teleported CNOTs for stabilizers that span nodes. The circuit-level noise simulations with BPOSD decoding provide the first insights into networked realizations of these codes. It's an important practical pathway for near-term hardware that can't yet support the long-range connectivity LDPC codes ideally want.
There was also a paper on writing QLDPC codes on programmable 2D toric architectures from Liu, Tsunoda, Zhui, and colleagues. That seems to be tackling the same connectivity problem, but from a hardware co-design angle.
Yes, and it's a clever solution. They use a 2D toric network of oscillators as a flexible communication fabric linking qubits at each site, which reduces the number of long-range couplers required from the order of n to an order of square root of n. They use dual-rail qubits with native gates including swap-weight swap and beam splitter swaps for high-fidelity long-range operations. Their qubit layout and routing algorithm exploit code symmetries to enable maximum parallelism. The circuit-level simulation with realistic noise modeling shows a logical error rate per logical qubit per cycle of 3% for the 1844 BB code, 2.6 times better than the best existing experimental result. It's a practical roadmap that identifies the key technological advances needed for low-overhead fault-tolerant computing at scale.
Let me shift to something that generated a lot of buzz, like the quantum advantage paper from Zhao, Zlokapa, Neven, Babush, Preskill, McLean, and Huang on exponential quantum advantage in processing massive classical data. That's a strong claim. What's your read on it?
This is probably the most theoretically significant paper of the month. They prove that a small quantum computer of polylogarithmic size can perform large-scale classification and dimension reduction on massive classical data, while any classical machine achieving the same prediction performance requires exponentially larger size. The key algorithmic innovation is quantum oracle sketching, accessing the classical world in quantum superposition using only random classical data samples combined with classical shadows to construct succinct classical models. They validate this on real-world applications, including single-cell RNA sequencing and movie review sentiment analysis, demonstrating 4 to 6 orders of magnitude reduction in size with fewer than 60 logical qubits. Crucially, this advantage persists even if BPP equals BQP and relies only on the correctness of quantum mechanics. It's a rigorous, provable advantage, not a heuristic claim.
That's a striking contrast to the quantum kernel SVM benchmarking paper from Kakavan, Strohmeyer, and Schlotter, which found essentially no statistically significant quantum advantage over classical baselines across 970 experiments. How do you reconcile those two results?
They're actually not contradictory. They're measuring different things. The Kakavand et al. Paper is an empirical study of near-term quantum kernel SVMs on tabular data with current noisy hardware. Their key finding is that dataset choice dominates performance variance at 73%, while kernel type accounts for only 9%. The spectral analysis is illuminating. Current quantum feature maps produce eigenspectra that are either too flat or too concentrated, missing the intermediate profile of the best classical kernel. The Zhao et al. Paper, by contrast, proves a complexity-theoretic separation that holds in the fault-tolerant regime with logical qubits. So the empirical paper tells us where NISQ quantum kernels stand today, which is not competitive, while the theoretical paper tells us where fault-tolerant quantum ML could go. Both are honest and important.
The noise-enhanced quantum kernels paper from Huang, Yang, and colleagues in Taiwan adds another twist. They find that operational noise can actually be beneficial for quantum kernel performance. That seems counterintuitive.
It is counterintuitive, but their explanation is plausible. They build analog quantum kernels and hybrid quantum kernels and find that noise improves expressivity and model complexity. It's essentially acting as a regularizer or a source of richer feature maps. They demonstrate this on benchmarking tasks and on estimating non-Markovianity from sparse data. The connection to the Kakavand et al. Spectral analysis is interesting. If current quantum feature maps are too flat or too concentrated, adding noise might shift the eigenspectrum toward a more useful intermediate profile. It's a provocative result that suggests noise isn't always the enemy in near-term quantum ML.
There was a fascinating paper on quantum computation at the edge of chaos from Hashizume, Wang, Schlaven, and Jaksch. The idea of using topological entanglement entropy as a regularizer to address barren plateaus in variational algorithms is quite novel.
This is one of the more conceptually creative papers of the month. They introduce quantum sparsity as a design principle, minimizing quantum information shared across multiple parties, and implement it using topological entanglement entropy as a cost function regularizer. The key insight is that a non-negative TEE corresponds to states with sparse structure in a suitable basis, while a negative TE signals untrainable chaos. So the regularizer guides optimization along the critical edge between these regimes. They also derive a quantum Nyquist-Shannon sampling theorem that bounds resource requirements and error propagation in variational algorithms. Numerically, the TE regularizer shows significantly improved convergence for complex data encoding and ground state search. It's a principled approach to a problem, barren plateaus, that has been a major obstacle for variational quantum algorithms.
The Quantum Architecture Search Review from Situ, He, and Lee covers the automation of variational circuit design. How does that connect to the broader theme of automating quantum software engineering?
They connect very naturally. The QAS review surveys how to automate the discovery of high-performing circuit structures for variational algorithms, covering reinforcement learning, evolutionary methods, differentiable search, and more. The Automated Quantum Software Engineering Review from Siavash and Moyne takes a broader view, covering the full life cycle of quantum software development, including hybrid quantum classical applications. Both papers are responding to the same underlying challenge. There are very few people with the expertise to design quantum algorithms and circuits from scratch, so automation becomes essential for scaling the field. The QAS work is more technically focused on circuit structure, while the software engineering review is more concerned with the entire development and deployment pipeline.
The MCP server paper from Shiraishi, Hamamura, Ishigaki, and Kadawaki is an interesting practical contribution, using a model context protocol server to let LLM agents autonomously execute quantum computing workflows. Is this the beginning of AI-driven quantum research automation?
It's a concrete early step in that direction. The key contribution is bridging the execution gap. LLMs can already formulate hypotheses and design experiments, but executing quantum algorithms requires managing QPUs, HPC clusters, and complex resource orchestration. Their MCP server lets an LLM agent process natural language prompts and autonomously invoke quantum computing tools, including sampling, expectation value computation, and execution on remote hardware via the Quantinuum emulator through Q2Q. The ABCI-Q hybrid platform integration is particularly interesting. The broader implication is that AI agents can abstract away hardware complexity through standardized interfaces, which connects to the OpenQSE reference architecture paper that's trying to standardize QHPC software stacks more generally.
Speaking of standardization, the OpenQSE reference architecture survey from Shahata, Austin, Beck, and a large team seems like a significant community effort. What's the core problem they're trying to solve?
The core problem is fragmentation. Quantum resources are increasingly integrated into HPC and cloud environments, but the software stacks remain isolated, proprietary, full-stack solutions without common interfaces. They analyze 9 production QHPC stacks and identify consistent needs in runtime abstraction, resource management, interconnect semantics, and observability. The OpenQSC reference architecture defines layer boundaries that allow different implementations to interoperate while preserving deployment flexibility. Crucially, it's designed to support both current NISQ workloads and future fault-tolerant systems without requiring changes to upper-layer application interfaces. The QDMI paper from Bergholzer, Walter, and colleagues on integrating IQM systems into HPC environments is essentially a concrete implementation of exactly the kind of standardized interface OpenQSC is advocating for.
The application-level benchmarking framework from Abumrad, Girotto, Goings, and a large team also seems critical for making cross-platform comparisons meaningful. How does it differ from existing benchmarking approaches?
Most existing benchmarks focus on low-level metrics like gate fidelity or qubit coherence times, which don't tell you much about whether a quantum computer can actually solve a useful problem. This framework presents 13 benchmark families that reflect realistic workloads across multiple domains and evaluates quality of solutions, total execution time, total energy used in time to solution. The benchmarks are designed to be reproducible and interpretable across stakeholder groups, researchers, engineers, and decision makers. The Exascale simulation paper from Montanes, Barrera, and Michelson is a nice complement. They use Jupiter, Europe's first exascale supercomputer, to benchmark Quantinuum Helios 1 using LRQAOA, finding coherent performance up to 93 qubits before the outputs become statistically indistinguishable from random sampling.
The Silicon Quantum Processing Unit from the HRL Quantum team is a major hardware paper. A 54 quantum dot array with a cryogenic CMOS controller and superconducting ribbon cable. That's a very different engineering approach from trapped ions or neutral atoms.
It's a landmark paper for the silicon qubit community. Exchange-only qubits are attractive because of their control signal simplicity and compatibility with advanced semiconductor manufacturing. You can potentially leverage the entire CMOS fabrication ecosystem. The HRL team integrates a custom cryogenic CMOS controller, a novel high-density superconducting ribbon cable, and a low-noise EO qubit device. They demonstrate qubit performance for both single qubit and entangling operations that advances the EO state-of-the-art by an order of magnitude and validate the system with a distance 5 repetition code and a quantum error detecting code. The 18-qubit configurable array is still small, but the engineering approach, solving the wiring and control problem at the chip level, is the right direction for scaling.
The parallel entangling gates paper from Diaz, Mohammadi Arzana, and colleagues on trapped ions demonstrates graph pattern-agnostic parallel gates with fidelities comparable to single-pair gates. That seems like a key capability for practical quantum advantage.
Exactly. Parallel processing is essential for practical quantum advantage, and this paper demonstrates it in a trapped ion system in a particularly clean way. For disjoint qubit pairs, the execution time of their parallel gates is comparable to a single-pair entangling gate, giving approximately linear speedup. For star and ring graph patterns, they maintain fidelities comparable to single-pair gates. The graph pattern agnostic implementation is important because it means you don't need to redesign your gate scheme for each circuit topology. They also demonstrate the speedup on 3 well-known algorithms. This motivates architectures with multiple medium-length ion chains, which is a natural direction for scaling trapped ion systems.
The Parity Architecture QFT paper from Armin, Fellner, Alba, and colleagues claims a record process fidelity for the quantum Fourier transform on IBM Heron R3. What makes the Parity Architecture special here?
The parity architecture encodes quantum information in a way that avoids the need for swap gates to implement long-range interactions with gate, which is the main overhead in standard QFT implementations on hardware with limited connectivity. The speedup compared to previous swap-based methods scales super exponentially as O(xpn squared, which is a dramatic improvement. They achieve a process fidelity of about 10 to the minus 2 for a 50-qubit QFT on IBM Heron R3, which is a record. They also show that including iSwap gates in the instruction set can improve scaling further. It's a compelling demonstration that architecture-aware compilation can unlock performance that generic approaches miss.
Shifting to the quantum security landscape, there were several papers on post-quantum cryptography. The Quantum Cryptographic Co-Evolution paper from Kundu and Compeller introduces a 2-dimensional coordinate system for mapping the transition to quantum-safe cryptography. How useful is that framing?
It's a useful conceptual tool for policy and strategy discussions. The 2 axes are cryptographic resilience and computational capability, and the 4 quadrants map out the transition from legacy classical systems to quantum resilient architectures. The key concept is the quantum gap. The delta between when a cryptographically relevant quantum computer arrives and when quantum-safe adoption is complete, which they argue represents the highest systemic risk. The companion paper on cross-layer PQC analysis of the network stack is more technically rigorous. They prove that cross-layer cryptographic transformations form a bounded lattice, with some surprising findings like WPA2 personal providing better PQC posture than WPA3 personal. Together, they make the case that the migration to post-quantum cryptography needs to be treated as a system-level design problem, not just a component swap.
The quantum-safe IPsec paper from Vicente Garcia Brito and colleagues at Banco Santander and Partners is a real-world deployment. Hybrid QKD and PQC in a banking network. How significant is that practically?
It's quite significant as a proof of concept for the financial sector. They validate a hybrid architecture combining classical cryptography, QKD, and PQC within a dynamic multi-point VPN environment across a 5-node testbed spanning Madrid, northern Spain, and Mexico. The heterogeneous mix of DV-QKD and CV-QKD implementations, multiple technology providers, and mutually incompatible key delivery interfaces makes this a realistic stress test. The fact that they demonstrate flexibility, scalability, and interoperability across environments is important. It shows that quantum-safe communication in financial networks is technically feasible today, not just in theory. The 6G regulatory paper from IJAZ complements this by arguing that the regulatory frameworks for quantum-safe communication need to be redesigned from the ground up with cryptographic agility as a first-class design constraint.
There's an interesting paper on superactivation of quantum capacity. Now, the Berg and Parrington framework paper mentions it was used to demonstrate non-asymptotic superactivation for N-17 channel uses. That's a fundamental result in quantum information theory.
The Berg and Parrington framework paper is a beautiful piece of mathematical quantum information theory. They develop a systematic framework for exploiting permutation invariance via Schur-Weyl duality to reduce the exponential scaling of semi-definite programs. The symmetric seesaw method they introduce uses permutation invariant codes to compute improved lower bounds on channel fidelity over multiple parallel channel uses. The fact that this was used to demonstrate non-asymptotic superactivation of quantum capacity for N17 is remarkable. Superactivation is the phenomenon where two channels with zero quantum capacity can together transmit quantum information, and showing it happens at a concrete finite number of channel uses is a significant step beyond the asymptotic theory. They also release an open-source Python package, which is important for the community.
The Hamiltonian learning paper from Shin, Lee, and Oh on achieving Heisenberg limited learning without short-time control resolves what they call a prominent open problem. Can you explain why short-time control was considered necessary?
Previous Heisenberg limited Hamiltonian learning algorithms relied on being able to query the unknown dynamics for arbitrarily short times, essentially probing the system at very fine time resolution. This is experimentally challenging because of finite control bandwidth and transient pulse errors. Shin, Lee, and Oh show that you can achieve Heisenberg limited scaling even when every query to the dynamics has a minimum duration. The key ingredient is a method for emulating continuous quantum control using only lower bounded evolution times, which reduces the learning task to sparse pure state tomography. For logarithmically sparse Hamiltonians, they achieve the information theoretically optimal 1 epsilon scaling in total evolution time for any constant minimum evolution time. For many body systems, they show a quantitative trade-off between minimum evolution time and total evolution time. It's a clean resolution of a fundamental experimental constraint.
The Magnonic GKP states paper from Liu, Fadel, and Lee is quite exotic, preparing GKP states in a magnon mode coupled to a superconducting qubit via a microwave cavity. What's the appeal of the Magnonic platform?
GKP codes are powerful because their phase-space grid structure protects against small displacement errors in both conjugate quadratures simultaneously. The Magnonic platform is interesting because the geometric anisotropy of the magnetic crystal intrinsically squeezes the magnon mode. You get squeezing for free from the physics rather than having to engineer it. The cavity-mediated qubit control then realizes an effective conditional displacement interaction. 2 rounds of conditional displacement plus a qubit measurement yield 3 and 4 component GKP-like states. They also show how to implement logical poly, Hadamard, and phase gates. It's a proof of concept that hybrid magnon qubit systems could be a viable platform for bosonic error correction, with potential applications in both quantum computing and quantum sensing.
The erasure qubit paper from Liu Wang and colleagues using transmon qubits is another hardware innovation for error correction. The 500 microsecond logical T1 lifetime is impressive.
This is a very practical contribution. Erasure qubits convert dominant physical errors into detectable erasures, which allows higher fault-tolerant thresholds. The standard approach uses dual rail encoding, which requires extra qubit overhead, and tailored coupling. This paper shows you can operate standard transmon qubits as erasure qubits using the ground and second excited states as logical states with relaxation errors detected via an ancilla qubit through a microwave-activated 2-qubit swap gate. The 500 microsecond logical T1, 10 times longer than the physical qubit T1, post-selected with repeated mid-circuit erasure detection is a striking result. Single qubit gate infidelity on the order of 10 to the -4, and they demonstrate heralded Bell state generation between erasure qubits. The key message is that mainstream transmon arrays may already be capable of implementing erasure-based QEC without hardware redesign.
The loss-biased fault-tolerant QEC paper from Pecorari, Brennan, Kondov, and Pupillo addresses a very specific problem in neutral atom processes, Rydberg excitation hopping, and residual Rydberg population. How does loss biasing solve that?
It's a clever physical insight. In neutral atom processors, shorter QEC cycles are generally desirable, but they amplify platform-specific errors, specifically Rydberg excitation, hopping between atoms, and residual Rydberg population that doesn't decay fast enough. These create non-Markovian correlated errors that degrade logical performance. Loss biasing converts spurious Rydberg excitations into atom loss via mid-circuit ionization, essentially turning a hard-to-correct correlated error into an erasure, which is much easier to handle. This restores fault-tolerant logical error scaling for intracycle poly errors, and, combined with loss-aware decoding, can achieve optimal erasure scaling while enabling shorter QEC cycles with reduced hardware overhead. The implementation uses fast autoionization in alkaline earth-like atoms, which is experimentally realistic.
Let me ask about the quantum advantage in classical data processing paper in the context of some of the application domain papers. There were papers on fluid dynamics simulation, transportation optimization, and even cancer biomarker discovery using quantum ML. Are any of these near-term realistic?
The honest answer is that they're at very different levels of maturity. The quantum lattice Boltzmann paper from Ray Jojo, Iaconis, and colleagues is one of the more credible near-term demonstrations. They implement transport under non-uniform velocity fields on ion-Q trapped ion hardware, including a 64-qubit barium system, and they identify MPS shadow tomography as a promising approach to scale readout. The transportation optimization paper from Shu Niu, Jayakumar Nair, and Dixit is refreshingly honest. They conclude that decomposition methods, meta-heuristics, and reinforcement learning already outperform quantum methods for medium and large urban transport networks, and recommend hybrid frameworks where quantum methods support local combinatorial exploration while classical methods ensure system-level consistency. The cancer biomarker paper applies QML to lung cancer subtype classification, but the quantum advantage claims they are much less rigorous than the Zhao et al. Theoretical result.
The resource estimation paper from Campbell, Rines, Amole, and colleagues at Atom Computing provides a compilation-driven framework specifically for neutral atom hardware. What architectural trends do they identify?
Several important ones. Magic state production remains the dominant source of overhead for their benchmarks, but access to atom movement can save time on cultivation and transversal gates. As problem size grows, routing and qubit movement become dominant bottlenecks, which highlights the need for movement-aware compiler optimizations. They find that neutral atom architectures combining dual species arrays with controlled qubit movement offer a promising path toward near-term advantage on fault-tolerant devices. The framework is valuable because it provides a tight feedback loop between hardware design choices and practical application requirements. You can rapidly compare different architectural configurations against real workloads.
The entanglement scaling paper on MPS representations of smooth functions from Bohern, Lukin, and colleagues is quite mathematical but has practical implications for data loading. What's the key result?
The key result is rigorous asymptotic expansions for how entanglement decays across bonds in the MPS representation depending on the smoothness of the input function. Smoother functions have faster decaying entanglement, which means they can be represented by shallower quantum circuits. They use tensor cross interpolation to construct utility-scale quantum circuits in a compute and memory-efficient way and validate by loading heavy-tailed distributions, including Levy distributions, important in finance, on IBM quantum devices for up to 156 qubits. This is foundational work for quantum algorithms that need to load classical data because it tells you precisely what circuit depth you need as a function of the function's smoothness properties.
The adversarial quantum teleportation paper from Marbrook and Sanders takes an interesting foundational approach to justifying fidelity thresholds. Why does it matter how we justify those thresholds?
It matters because fidelity thresholds for quantum teleportation have been debated for years. The question is whether exceeding a certain fidelity actually proves that genuine quantum teleportation occurred or whether a classical cheater could fake it. Mabrouk and Sanders construct explicit adversarial models with cheating parties and show that the previously established average fidelity thresholds of 1/2 and 2/3 arise naturally from their adversarial framework. This gives those thresholds a rigorous operational justification. They represent the boundary above which a specific type of adversary cannot fake successful teleportation. The methods are also relevant beyond teleportation to other quantum information gadgets, which makes it a broadly useful, foundational contribution.
The quantum secret sharing paper from Yam, Wilkinson, Gendorfer, and colleagues at TU Munich is an experimental result on a superconducting microwave network. Surpassing the no-cloning threshold fidelity of 2/3 is significant. What does that enable?
Exceeding the no-cloning threshold means the protocol is genuinely quantum. No classical strategy can replicate it. In the 3.2 threshold scheme, they implement a secret quantum state is split among 3 players such that any 2 can reconstruct it, but 1 alone cannot. Surpassing 2/3 fidelity in the reconstructed state, even in the presence of an omnipotent, dishonest player, demonstrates unconditionally secure communication. What's particularly interesting is their experimental exploration of connections between QSS and other quantum information tasks, quantum dense coding and elementary quantum error correction of channel erasures. These connections suggest that QSS is not just a standalone protocol, but a building block for more complex quantum network functionality.
The post-cut metadata inference attacks paper from Punch, Gua, and Rodig is a security paper I didn't expect to see in this context. The idea that circuit cutting creates a metadata side channel is quite alarming.
It's an important and underappreciated security concern. Circuit cutting is used to run circuits that exceed a device's qubit capacity by decomposing them into smaller fragments. The insight from Punch et al. Is that the compiled metadata, fragment width, depth, 2-qubit gate count, observable by a semi-honest cloud provider constitutes a practical side channel. Operating solely on this provider visible metadata, they recover algorithm family with 96% accuracy, cut mechanism with 84.7% accuracy, and Hamiltonian K-locality with 96% accuracy. They validate on a 156-qubit production quantum computer. The key finding is that leakage is structure-dominated, not explained by scale artifacts. This means quantum cloud providers need to treat metadata privacy as a first-class security concern, not an afterthought.
There were also several education-focused papers. The Quantum Education Ecosystem Review from Metwali and colleagues, the undergraduate course textbook from Young, and the Qubit Quest gamification paper. What's your read on the state of quantum education?
The Metwali et al. Review is the most comprehensive. They analyze global initiatives and conclude that quantum education is more accurately a non-linear ecosystem than a traditional pipeline with multiple entry points and critical transition gaps. The key challenges are inequitable access, lack of standardized curricula, and limited empirical evaluation. Young's undergraduate textbook is a practical contribution for physics students who need a rigorous but accessible introduction with Shor's algorithm and quantum error correction as the main destinations. Qubit Quest from Hill and Morales Trujillo shows that gamification can genuinely improve learning outcomes for introductory concepts. Participants improved their understanding of the block sphere, entanglement, and quantum circuits, with those completing more levels achieving higher scores. The Lagrange paper from Viviani and colleagues at Links Foundation is also relevant here. They describe Italy's first publicly accessible quantum computer, which is being used by students at Politecnico di Torino during lectures and formal examinations.
The crossbench paper from Hawley and Shiu on crosstalk benchmarking, and the MCMIT paper from Geortimis and colleagues on mid-circuit measurement error mitigation both address practical NISQ hardware challenges. How important are these for near-term systems?
Both are practically important. Crossbench generates customizable crosstalk benchmarks for arbitrary NISQ device topologies using a custom graph labeling algorithm. The key value is accessibility. Crosstalk metrics are rarely provided by hardware vendors and are expensive to obtain, but they're needed for error mitigation, security analysis, and circuit translation. Their results show statistically significant identification of high crosstalk gates across multiple IBM devices. MCMIT addresses a different bottleneck. Mid-circuit measurements are essential for quantum error correction and distributed quantum computing, but they suffer from high error rates and latency-induced decoherence. Their hardware-software co-design reduces feedback latency by up to 70%, improves circuit depths by up to 7x, and achieves 37 to 73% higher discriminator accuracy for short measurement durations, leading to up to 80% lower logical error rates in QEC. Both papers are filling gaps that matter for making current hardware more useful.
The dynamical decoupling paper from Tong, Shirizli, Chen, Wang, and Pokerel on learning error suppression for dynamic circuits achieves a 3-fold reduction in dynamic circuit error rates. What makes dynamic circuits particularly hard to suppress errors in?
Dynamic circuits integrate mid-circuit measurement and feed-forward, conditional operations that are essential for efficient quantum algorithms and fault-tolerant computation. The problem is that these operations introduce measurement-induced errors and control constraints that conventional error suppression techniques weren't designed for. Standard dynamical decoupling sequences are derived theoretically for unitary evolution, but they don't account for the interruptions caused by measurements and classical feedback. The empirical learning framework from Chung et al. Optimizes DD sequences at the level of circuit subintervals and qubit subregisters, essentially learning what works for each specific dynamic circuit structure. The threefold reduction in error rates, demonstrated on quantum Fourier transform with measurement on chains of up to 20 qubits, is a strong result. The key finding is that empirically optimized DD systematically outperforms theoretically derived sequences for dynamic circuits.
Looking across all these papers, what do you see as the most important overarching themes of April 2026 in quantum computing research?
I see several converging themes. First, fault-tolerant quantum computing is moving from theoretical blueprints to concrete engineering. The walking cat architecture, the neutral atom FTQC designs, the silicon QPU, and the ultra-high rate codes all suggest we're entering a phase where the question is not whether FTQC is possible, but how to build it efficiently. Second, decoding is emerging as a critical bottleneck, and AI-based decoders, like both the neural decoder for LDPC codes and the pre-decoder for surface codes, are showing that machine learning can dramatically improve both accuracy and throughput. Third, the quantum advantage question is becoming more nuanced. We have a rigorous theoretical proof of exponential advantage for classical data processing, empirical evidence that NISQ quantum kernels don't yet compete with classical baselines, and honest assessments of where quantum optimization does and doesn't help for real applications. Fourth, the infrastructure layer. Standardized interfaces, benchmarking frameworks, compilation tools, and security is maturing rapidly. And fifth, the education and workforce pipeline is getting serious attention as the field scales.
That's a really helpful synthesis. One last thing, the What Quantum Computer to Buy paper from Krasnok is an unusual contribution for a research venue, but I found it genuinely useful as a procurement framework. Is that kind of practical guidance becoming more important?
Absolutely, and I think it reflects the maturation of the field. Krasnok's framework distinguishes 5 capability layers and separates peer-reviewed results from commercial offerings and public roadmaps, comparing superconducting, trapped ion, neutral atom, annealing, and photonic platforms through the lens of institutional fit and access model. The main conclusion, that most institutions should begin with the smallest layer of capability that produces repeatable near-term value and preserves strategic flexibility, is practical wisdom that's easy to lose sight of amid the excitement of research breakthroughs. As quantum computing moves from research curiosity to infrastructure, this kind of guidance becomes as important as the technical papers. It's a sign that the field is growing up.
This has been a really illuminating conversation, Bob. April 2026 feels like a month where multiple threads, hardware, error correction, algorithms, software infrastructure, security, and education all advance simultaneously and in ways that reinforce each other. The convergence of rigorous theoretical results like the quantum advantage proof for classical data, concrete engineering milestones like the walking cat architecture and the silicon QPU, and practical tooling like standardized interfaces and AI decoders gives me a sense that the field is genuinely accelerating. Thanks for helping me make sense of it all.
It's a great time to be in the field. The breadth of April 2026's output, from foundational results on quantum contextuality and Hamiltonian learning, to practical deployments of quantum-safe cryptography in banking networks, to gamified quantum education, shows that quantum computing is no longer a single-front research effort. It's an ecosystem. And as that ecosystem matures, the interactions between theory, hardware, software, and applications become increasingly productive. The papers we've discussed today are a good snapshot of that complexity. Keep reading, the pace isn't slowing down.